Welcome to this tutorial on Kubernetes Readiness Probes. In this video, you'll learn how to master traffic control to your pods using readiness probes. Readiness probes are essential health checks that ensure your applications only receive traffic when they're truly ready to handle requests. Let's dive in and explore how readiness probes work and why they're crucial for building reliable Kubernetes applications. A readiness probe determines whether a container is ready to start accepting traffic. Kubernetes uses this signal to control which pods receive requests from services. Think of it as a quality check before allowing customers into a store. Unlike liveness probes that restart containers when they fail, readiness probes temporarily remove pods from service until they're ready again. The pod continues running, but it simply won't receive any new traffic during this period. There are several important use cases for readiness probes. First, startup dependencies. Your application might need time to load configuration files, warm up caches, or connect to databases before it can handle requests properly. Second, rolling updates. Readiness probes ensure new pods are fully ready before old ones are terminated during deployments, preventing service disruption. Third, temporary overload. If a pod becomes overwhelmed or degraded, the readiness probe can remove it from load balancing until it recovers. Finally, external dependencies. When critical external services like databases become unavailable, readiness probes can stop routing traffic to pods that depend on them. Kubernetes provides three types of readiness probes. The HTTP GET request probe sends an HTTP request to a specified path and port. It considers the probe successful when receiving status codes between 200 and 399. The TCP socket probe attempts to open a TCP connection to a specified port. Success means the connection was established. The Exec command probe executes a command inside the container. It's successful if the command returns an exit code of 0. Each type serves different purposes, so you can choose the one that best fits your application's needs. Here's a practical example of an HTTP readiness probe configuration. The HTTP GET section specifies the path, which is /health/ready, and the port, which is 8080. You can even add custom HTTP headers for authentication or other purposes. The initial delay seconds parameter tells Kubernetes to wait 10 seconds after the container starts before running the first probe. Period seconds is set to 5, meaning Kubernetes will check every 5 seconds. Timeout seconds is 3, so each probe must respond within 3 seconds or it's considered failed. Success threshold is 1, requiring just one successful probe to mark the pod ready. Failure threshold is 3, meaning 3 consecutive failures will mark the pod as not ready. Let's understand each configuration parameter in detail. Initial delay seconds defines the wait time before the first probe after the container starts. This gives your application time to initialize. Period seconds determines how often Kubernetes performs the probe check. Timeout seconds specifies the maximum time to wait for a probe response before considering it failed. Success threshold indicates how many consecutive successes are needed to mark the pod as ready. Finally, failure threshold sets how many consecutive failures occur before marking the pod as not ready. Properly tuning these parameters is crucial for reliable traffic management. Let's walk through how traffic control works with readiness probes. First, Kubernetes continuously checks the readiness probe based on the period seconds configuration. Second, if the probe fails for the number of times specified in failure threshold, the pod is marked as not ready. Third, the service immediately removes the pod's IP address from its endpoints list. This means the pod is taken out of the load balancer rotation. Fourth, no new traffic is routed to the pod, but importantly, existing connections are allowed to continue. This graceful handling prevents abrupt disconnections. Once the pod passes the readiness probe again, it's automatically added back to receive traffic. Following best practices ensures your readiness probes work effectively. Always set initial delay seconds to allow adequate application startup time. Use lightweight endpoints that check actual readiness, not just whether the process is alive. Keep probe checks fast to avoid false positives caused by timeouts. Set an appropriate failure threshold to handle temporary glitches gracefully without immediately removing the pod from service. Include checks for critical dependencies like databases and external APIs in your readiness logic. Finally, monitor probe metrics to tune parameters based on real behavior. These metrics help you understand how your application performs and optimize probe configurations accordingly. Let's discuss common pitfalls you should avoid when working with readiness probes. First, having no readiness probe defined means pods receive traffic immediately, even if they're not ready, leading to errors. Second, too aggressive timing with short timeouts or low failure thresholds causes flapping, where pods rapidly switch between ready and not ready states. Third, expensive probe checks that perform complex operations slow response times and waste resources. Keep your probes simple and fast. Fourth, making readiness probes identical to liveness probes is a mistake. Readiness should check if the application can serve traffic, while liveness checks if the process is alive. These are fundamentally different concerns and should be configured differently.
If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.